Hello everyone. So in this lecture we want to further simplify this equation, spectral equation that we obtained in the last lecture, and to gain some insights into each of the terms that are present in this equation. Okay, so again, it's a little bit difficult to draw some pictures from this FII function. So in order to simplify that, we define 3D spectral function by integrating this over spherical shells of radius k. So instead of looking at this k border, which has k vector, which has three components, we are going to only convert it into one component. Okay, so the way we are going to do is by defining 3D spectral function, and the way it is defined is as follows. So we define it E, K, and T is defined as 1/2 the integral of K equals to the absolute of K vector of Fii, this function that we got, Kt dsk. So let me explain a little bit further what does this mean. So it is, the reason we do that is that it is difficult to draw pictures from FII. Okay, so let me put this here down. So it is difficult to draw pictures from FII here, the thing that we got here. So we define the integral of Fiik and T over spherical shells of radius k equals to absolute of k. Okay, using this formula here, we define that. So the way actually what it means is that here, say we have all these three-dimensional wave numbers in 3 dimensions like x, y, z. We're going to have 3 wave numbers, right? So let's say this is the first dimension. Second dimension. And third one. So we have K1, K2, and K3. Okay. So the way we define this is that we are going to integrate over spherical shells of radius k equals absolute of k vector. So say here it's going to look like something like this. So we have these spherical shells here. All over these spherical shells, we take these integrals So for each of these spherical shells, the radius is absolute of k. Okay. So we take the integral over these this radius, okay, of these spherical shells, and we know that k squared is going to be k1 squared plus k2 squared plus k3 squared. Okay. So we define this 3D spectral function ek to kind of simplify. So instead of looking at each of these components, k1, k2, k3, we just look at this k by integrating over spherical shells of radius k equals to the absolute value of that k. Okay, so this will convert the 3D EKT, the 3D spatial function of EKT, to one-dimensional in space. Okay, so this is going to much further simplify, because now we are going to only have one dimension k rather than a vector that has 3 dimensions. So now, based on this definition, let's integrate over spherical shells of radius k. So if we integrate this equation, let's integrate that. So we have, based on this definition, 1/2 integral k equals to absolute of k of partial fi I k bar t kt and ds over those surfaces with k. Okay, so we take that integral over that surface equals to 1/2 the integral over k of the second term, which is gii. So it's gii kt dsk minus the dissipation term, so the dissipation is minus 2 nu k squared. So we have minus 2 nu k squared 1/2 the integral over k fi I kt and ds k. Okay, let's see what's going on here. Okay, so now let's see what we have. So here, this term, we define this as just as a definition, we just write this as t, k and t. And this we know based on the definition that we already made. This is the 3D spectral function here. We just define it, right? So it's going to be EKT. And we should also count for this 1/2. So this is going to be EKT. So the equation, and this term is also EKT here, but the time derivative of that. So what we are going to get is as follows. We are going to get partial over partial t of E kt equals to t kt minus 2 nu k squared e k t. Okay, this is very famous equation in turbulence. And now we have kind of simplified this complicated equation FII into this a simpler equation that we can better understand what does this mean. So again, this E is 3D energy, a spectrum function, and this T is nonlinear spectral energy transfer function. And the last term is, of course, the dissipation, okay? Related to the dissipation. So now I want to gain more insights into this equation. Okay. So here, the left-hand side, the LHS, is the rate at which energy changes at any given wave number. Okay? So what does this mean? This means that at any wave number here, this shows how the energy at that wave number is changing with time. Okay? So now if we take the integral, let's say for E, I want to see what is E. If we integrate over all wave numbers, we are going to get the rate of change of kinetic energy with time. The rate of change of whole kinetic energy, right? Because now we are integrating over all wave numbers, so we are going to get the whole energy, the whole kinetic energy with time. So for example, this turbulent kinetic energy that we defined as 1/2 q square bar, we can get this by simply taking the integral over all wave numbers from 0 to infinity of this 3D energy spectrum function, E k t dk. So in other words, if you take this, the integral of the energy over all wave numbers in this space if you take all these, the integral over all these wave numbers in the whole space, then you are going to get the total kinetic energy, turbulent kinetic energy in the system. So that is what this means. This 3D energy spectrum function has actually shows the contribution of each wave number to the turbulent kinetic energy in the system. And if you add and sum and integrate over all wave numbers, we are going to get the turbulent kinetic energy in the system. Okay? So now what I'm going to do is take an integral of this equation and to gain further insights in the next session, and then talk about Kolmogov's idea about the role of each term, especially the nonlinear spectral transfer term, what it does, and also plot draw how these terms actually look like when you draw them versus the wave number and energy, and how do each of these terms and what do each of these terms actually do. Thank you, everyone.